Welcome to the Insightful Professor. Today we continue our lecture series on Introduction to Database, and the topic today is RDBMS case study. We're going to be looking at the Oracle database. In this discussion, we're going to demonstrate some of the concepts that we may talk about as kind of being abstract or theoretical that apply to database, and we're going to show how these actually are used in practice by looking at a commercial relational database management system product. We're going to provide some working examples of SQL statements, which will include data definition. We'll be creating some tables and indexes, show you the statements that will accomplish that. We'll look at data control, where we're looking at security and authorization. And we'll look also at some simple examples of data manipulation. Insert, update, delete, and we'll throw select in there as well. We'll examine how a DBMS addresses data integrity, a very important aspect of what the database system does for us. We'll look at declarative integrity constraints, and we'll suggest an alternative through what's called procedural integrity. We'll introduce the basic syntax of the SQL select statement for data retrieval, and we'll also discuss the idea of the system catalog in more detail than just being a very high-level overview. We'll show you some of the metadata. Oracle refers to this system catalog as the data dictionary. So we hope that by examining a commercial product in action, you'll be able to see theory being put into practice. So we'll begin with an examination of a commercial relational database product, kind of seeing some of the aspects of the concepts that we discussed previously put into action. And later on, because this product is based upon relational theory, we'll consider the actual theory, the relational model that underlies a system such as Oracle database. So students will be given the opportunity to work with a database system early in the course. That's the benefit that we give by giving you the commercial product up hand. Instead of just dumping theory and abstract concepts, you'll get an opportunity to roll up your sleeves and actually try these things out. The theory, rather than being presented early, is presented later, and students can, I believe, appreciate it much more by having worked with the system, kind of kick the tires, see how things work, and then suddenly say, aha, this is where the theory says that we have to do it this way. Now it makes sense. So we'll also address how to design a database after we've had this experience of kind of kicking the tires on the system. So that's the way I structure my course when I present it in an academic setting. And that's the approach I'm obviously going to be taking here. So why did we choose Oracle database for our case study? Well, Oracle database is a relational database management system, or an RDBMS, and it turns out to be one of the most popular commercial database management systems in the world. It's used all over the place. And in fact, I've had opportunities to present training on Oracle specifically in person throughout the United States, throughout Canada. I've actually been over to England as well and done some training over there. In addition, I've done training for Oracle remotely, that is like a virtual classroom, distance education, where I've had students in Africa, Mexico, India, various European countries. So I know the product is used all over the place. So Oracle database operates on many different systems, from large mainframe computers down to personal computers, running on operating systems such as ZOS, various flavors of Unix and Linux, and also Microsoft Windows. The neat thing about this product is, regardless of which which operating system you're using, what we have is the DBMS presents the same look and feel. That's pretty neat. So if you're working with a Windows implementation or a Linux implementation, it's going to look very much the same if you're a user or application developer, perhaps even to the database administrator. But obviously, once the database administrator gets down to the nuts and bolts and the operating system file services, they're going to see a difference. In addition to the DBMS, Oracle, like other vendors of commercial relational products, offers some additional pieces of software, Sometimes they're free, they're kind of built in. Sometimes they're additional license, so you got to cut another check for that. But they give you more software than just the DBMS, or make more available. So for example, what we have with Oracle is an interactive SQL interface, a text-based tool or command tool called SQL Plus. It's a command line interface, and this is kind of old faithful. This has been around for a long time. I've been working with Oracle since Oracle 5. We're now up to Oracle 12, and Oracle 18 is out. And this tool is still around. SQL Developer. It's an interactive tool. It also has case capability, computer-aided software engineering, where what we can do is we can get a data modeling component here, and we can design databases with this. It's not a full-fledged graphical interface or GUI type of tool, but it's probably a lot friendlier to work with for most folks than the command line tool of SQL+. Enterprise Manager is a graphical type of database administration tool. Then we have what are called pro compilers. These are actually what are called pre-compilers, but Oracle calls them pro, for Pro C, Pro Ada, Pro Fortran. For the various programming languages, there are specific pre-compilers that take the SQL that's been embedded and then translate those SQL statements to calls to various entry points within a database, but making those calls in whatever the language is. C, COBOL, Fortran, Ada, whatever, and it makes the call valid syntax in that language. You have to do this before you pass your code onto what's called the host language compiler. That's why they call it a pre-compiler. Then development tools. These are not free, but they're nice tools. Oracle Forms and Oracle Reports. Forms is a graphical type of editing tool for generating graphical applications. Originally, this was deployed as client-server. Now these tools produce products or finished products that are in a 3-tier or N-tier environment, where you have a client, an application server, and on the back end, the database server. So these are actually very nice tools. Utility programs. Most database management systems provide capabilities like this. Oracle has a load utility, which they call SQL Loader, which allows you to take data that exists outside the database and bring it into tables in your database and populate those tables. There's also an import and an export utility. These can be used for moving data around and also for doing kind of logical backups. Oracle Net is a communication software, and this is very good if you're dealing with client server, which most people are, and distributed database. So again, additional software that's available to you in the Oracle world. Let's take a look at the logical view of Oracle. What we have is we have various front-end tools. The front-end tools could be a C program or COBOL or Ada or whatever that we wrote that contains calls to the database in the form of embedded SQL. We could also have an interactive front-end tool that allows a user to sit down without needing to write a program. They can simply write instructions in this language of SQL, and the database then will process those. We could also have more of a graphical tool, such as an Oracle Forms application. And Oracle Forms also would have embedded SQL statements within it. The point is that there are a variety of different ways to interact with the database, but all of our requests are kind of funneled through the database management system, or the DBMS, and those requests are presented to the database management system using a common language of SQL. The DBMS will then process the SQL and go against the database out on disk, communicating with the operating system to gain access to the files, take the data, maybe putting it out to the database or reading it if it's a query such as a select statement, and then bringing that database here, maybe massaging it in some way. There might be additional function calls within the SQL statement. And then finally, the data that was requested is returned to whatever that requesting application is. Notice, though, that all requests must go from that front-end application through the DBMS in order to gain access to the data. it is not possible to write a program that goes directly against the data and kind of circumvents that middle layer of the DBMS software. So that DBMS software actually does a lot for us in terms of protecting the database, because it's providing security, integrity, and so forth. And that's why all of our requests go through that. So it's an additional piece of software, but that piece of software does a lot of work to kind of justify its existence. Well, what is a relational database management system, or an RDBMS? We've mentioned this term a few times, but we haven't really explained what it is. Well, an RDBMS is based on what's called the relational model. This is a theory that was put forth by a researcher at IBM, E.F. Codd. Back around 1969, 1970 is when we see the theory being presented to the world. Since then, commercial products were developed. IBM did some prototype research in the mid-1970s, headed by Donald Chamberlain. They developed a system called System R, which took Codd's relational theory and tried to see, well, can we actually put the theory into practice and make a database management system? Turned out they could. And as a result, products like IBM's SQL DS and IBM's DB2 came out in 1983, 1984. Then you saw Oracle coming out in the 80s. And down the road, you saw SQL Server. And there have been a whole bunch of other products that have come out that have all been written based upon this same theoretical foundation. So what does this theory do for us? Well, it establishes the criteria for what we call the logical structure of the data within a database. This would be how users and applications see the data. This is said to be logical. It says nothing about how it's physically stored within the computer, but this is how users and applications perceive the data. Additionally, the relational model provides a set of operators to manipulate that structure. The theoretical language or abstract language that Codd talked about was the relational algebra. He also talked about the relational calculus. These languages were the manipulative part of the model to operate on the logical structure. The language that we'll be seeing is based upon these theoretical languages. The language is SQL. The model also addresses what's called database integrity, and we'll talk about that in this section. So Oracle database is generally considered to be faithful to this theory. There are some aspects of the model that might not be supported by Oracle, and that same could be said for DB2 and SQL Server and any other relational product. But there's also some shortcuts that may have been taken. So in general, these commercial relational products such as Oracle, DB2, SQL Server, MySQL, Informix, and the list goes on and on and on. They are all based upon the underlying relational theory, and generally they're rather faithful to that theory. Let's look at the relational data structure. We said this was the logical structure that users perceive when working with a relational database. The user sees the data as a collection of tables, kind of rows and columns. That's what we think of when we say table. We have a bunch of rows, and each row will have kind of subdivisions in terms of columns. So looking at the idea, if you're familiar with traditional data processing, we talk about storing our data out in operating system files. And what we store is one record for one particular thing. So if we have an employee file, we have within that a record for Mo, who's an employee, a record for Larry, another employee, a record for Curly, a record for Shemp, and so on. We have one record that has the data items that describe each individual employee. Then within a record, we have fields or data items. We might have the employee's first name, the employee's last name, the employee date of birth, the employee date of hire, and so forth. So the analogy that we draw here, if you're comfortable with that terminology for traditional data processing with files, would be that a table is logically equivalent to or analogous to a file. Because when you go to read data, you first access a file and you read from the file. Well, when you have a relational database, you'll be reading your data logically from a table. We're not saying this is the physical implementation. Remember, we're saying tables are what we kind of perceive. How it's built under the hood, we don't really have any idea, and we need not be concerned with that. Then, when we write, we also write data to a file, or we write data to a table. That's the target of our output operation. Similarly, when we talk about a row containing a description of one individual, that was analogous to a record within a file. And a column is analogous to a particular field or data item. So a table is given a name when it's created, and the table generally holds data about one type of real-world object or entity. This is said to be what's called a normalized database design. We store data about one kind of thing and one kind of thing only in a table. Then, if we need other data, we go to another table. And if we need to bring the data from one table and data from another table together to answer a complex business question, we do that with an SQL statement. But the idea is we're storing the data about one kind of thing in one place, data about another kind of thing in another place, and so on. And it makes it very clean, very stable. This is called a normalized database design. And for operational data stores or transactional databases, this is the preferred way to go. Now, here's a little example of a table that we have in our academic database environment. What we have is a table called staff, kind of an employee table. Here are the names of the columns. There's a column called e-name, e-title, e-salary, and department. E-name contains the name of an employee. So when we talk about the table, we talk about columns, we talk about rows. Here's the big picture. Notice the data type would be character for e-name and e-title. It would be numeric for e-salary. So let's go a step further and look at this, kind of breaking it down into pieces. Each column contains a single atomic data item. And by atomic, we mean whatever value you have in here, such as Luke or Dick Nix or Euclid. Those character strings are treated as a unit by the system. The system treats that whole series of characters as one chunk of data. We can operate on that with various functions and manipulate it, but when we store the value, we're storing a chunk of data as a character string. When we retrieve it, we're treating it that way. So an atom was considered at one time to be the smallest unit of data. It was non-decomposable. And that's where the term atomic comes from. So that's the idea of what we have here. We're treating this unit of data as one chunk. Each column contains data of just one type. So all the values in here are character. Go back to the table that we looked at a moment ago. All the values in salary are numeric. There are other data types where we could have date-time values. We could have timestamps. We could have dates and so forth. We could also have other types of numeric data. We're not limited to just number as a broad category, but what we can have is we can distinguish between integer. We can distinguish between floating point and decimal and so forth. But whatever we designate when the table is created as the data type, all the values stored in there in the various rows will have to be of that same type. Each column has a name, and that name must be unique within the table. You cannot have two columns in the same table that have the same name. That name could be used for the name of a column in another table, but when we talk about one table, all the column names must be unique. The left to right order is not important, and what I mean here is I'm displaying e-name as the leftmost, then immediately to the right, e-title, e-salary, and department. That's not carved in stone. There's a concept here of data independence that allows us to select the columns and present them back to the requester or to the application in any left to right order that we wish. So if I wanted to, I could have put e-title as the first column being displayed. Then I could have put department, then e-name, then e-salary. I could have moved these all around. So the order in which we return the columns or work with them is not important at all. Obviously, we have to establish some order when the records are stored, but that's physical. And the whole point of the relational model is there is a clear separation between logical and physical. Logical, remember, is what we're working with here. We're seeing the data as a table, and we're manipulating that table. Physically, how it's stored under the hood, don't know, don't care. So the idea is that's where we don't have to worry about the left to right order. Now, let's look at the table broken a different way. We're going to look at an individual row. Rows don't have names. Rows can be stored in the table or returned in our result for display in any order. So the rows are unordered within the table. They don't have names, and for each column, a row stores a single value for that column. And that's the basic idea. So when we talk about something like a staff table, we're talking about storing data about all of our staff or employees. Then when we look at an individual row describes data about one particular instance, one particular staff member, or one particular employee. That's the idea of what a table does for us, and the row and the column. So essentially, that's the logical structure. When we talk about theory of relational model later on, we'll go into this in more detail and take a very different slant on it. But again, from the usability standpoint of a relational database, that's all we need to know. Now, the second part of the relational model is a set of operators or a language to work upon or manipulate the logical structure. In our case, the language that we'll see is SQL. This is not the language that Cod talked about. This language came about through the research being done largely at IBM for that System R prototype back in the mid-70s. This language is called SQL, or the Structured Query Language. Originally, IBM researchers had called it SQL, S-E-Q-U-E-L. Turned out there was some kind of a copyright with that, and this language became SQL, Structured Query Language. This has become the standard relational database management language. It's used by Oracle, and it's used by most other commercial relational database management systems. The system has evolved a great deal over the years. The first official standard came out in 1989, modified in 92, 1999, and then it continued to evolve. 1999 is probably where it kind of plateaued a bit. I don't think there have been very many significant enhancements beyond that, even though there have been additional versions of the standard that have come out. But when we talk about the standard, we're talking about the committee called ANSI, the American National Standard Institute, and there's an ANSI SQL standard. Ideally, we'd like to write our code such that we can write it one way and it works on all these different platforms. That's kind of the rationale behind the standard. Doesn't quite work that way in practice because there are some aspects of the standard that are not supported by vendors, and then the vendors add their own bells and whistles that aren't part of the standard. But it's a nice idea. It's kind of nice to think about nice things like that, good things. Anyway, now talking about SQL, if you're familiar with third-generation programming languages like perhaps COBOL or C, you have a general feel for how languages work when doing things like I/O, input-output operations. And you're also maybe acquainted with, if you've been around for a while or read some history books, hierarchical and network database management systems. Those have a very different way of presenting the structure to users and programmers of those respective databases. The point is, from those environments, that's what the world has worked with for a great deal. SQL does things in a different way. SQL is said to be a non-procedural language. And what this means is, with non-procedural, we don't have constructs such as if, then, else, do, while, do until, or our good old go-to that you might see in many languages, because those are kind of directing the flow of activity within programming languages. SQL is not a programming language. It's a database sub-language or query language primarily. So SQL is said to be non-procedural. A bit more on that in a moment. SQL is also a language that supports set-level processing. In contrast to this other environment with third-generation programming languages and hierarchic and network databases, When you perform an I/O operation in those environments, you're manipulating a single record at a time. When you do a read, you get one record. When you do a write, you write one record. Single record operations. With SQL, you operate on a set of data at a time. Very different way of thinking. And it's something you have to be aware of. Even if it makes sense to you, you've got to think about it when you're writing some of the SQL statements. And we'll bring that up a little bit later. Okay, what is non-procedural? We say a requester identifies what they want in the terms of which rows and which columns. They're kind of saying, this is the data I want, kind of pointing it out. They don't say how to get it. So how might you go and get the data? Well, if you think about various data structures that you might have worked with if you've taken a data structures course, or if you've worked with a hierarchic database or a network database, you are actually giving instructions to the system of saying, okay, from here, go over there, then do this, and then do that, and follow this pointer or whatever. You're giving detailed descriptions, or you're defining a process or procedure to be followed to get the data. That doesn't happen in a relational database. With a relational database, you just say, this is what I want. You don't have to worry about saying how to get it. So in that sense, SQL could be considered a descriptive or a declarative language. You're declaring what the result will look like, but you don't give any explanation of how to get it. So how does the result come back? It's kind of like magic. Well, actually, it's not really magic. What it is there's a component in a relational database called a query optimizer. And the query optimizer takes the what that has been specified, and it figures out how to process the data. For example, if it requires accessing 2 or 3 tables, join operation will have to be performed. But there are different flavors of join. There's what's called nested loop join, there's merged join, there's a variety of join techniques that can be used. And what we see is the optimizer figures out which technique to use. In fact, join order. If you've got 3 tables, you can join table 1 with table 2, and then table 1, 2, the combination, with table 3. Or you could start with 3 and join it with 1 and so forth. The end result will be the same, but the intermediate steps might involve considerably more or less work depending upon the order in which things are done. We don't have to worry about that. That's what the query optimizer does. So the query optimizer decides what kind of join to do, join order, and other things as well. So that's pretty neat. So a SQL statement effectively then describes or declares what the result of the query will consist of, but doesn't say how to bring that into existence. That's the query optimizer's job. Now, set level processing, the other major characteristic, means that a requester identifies many rows, a whole set of rows, by saying, for example, I'm interested in all of those staff members who work in the theology department, or all of those staff members who have a salary greater than 500. You're not saying one, but you're saying everyone who qualifies comes back. That's a set of rows. This becomes such that the language is much more powerful, much more expressive than traditional third-generation languages and record-at-a-time type of environments like hierarchic and network databases. And this is something that encourages or supports the idea of query optimization. Now, with SQL, there are different aspects to the language. There's a subset of operations within SQL called data definition. We refer to these commands as comprising what's called the data definition language, or the DDL. These instructions are used to create objects, drop objects, or maybe change characteristics of the object, modify or alter these objects that already exist. The operations are generally going to be performed by a database administrator. So users, application developers generally don't do data definition. That's the database administrator. Data control, DCL, the data control language. These operations are used to control permissions or authorizations. We can grant authority or permissions or privileges to a user that enables them to be able to perform certain operations, or we can revoke privileges, kind of retract the grants, and now those users can no longer perform those operations. Again, who does this? Could be the database administrator, could be a separate individual who might be a security officer. But generally, this is not something done by the masses. This is not something done by users or developers. The third category is kind of like SQL for everybody. Data manipulation, and this falls into the realm of DML, or the data manipulation language. The operations that fall into this category are used to retrieve data, insert data, delete or update. So we can take existing data and examine it, retrieve it for some kind of analysis. We can add new rows. We can delete existing rows. We can modify rows, maybe changing one or more column values. These operations, especially when you consider data retrieval, if you believe that to be data manipulation, that's the way I group it, this then is going to be something used by effectively everybody. The DBA will do data retrieval. Users will do data retrieval. Application developers will do data retrieval. Application developers will also perform these other operations, and perhaps DBAs will perform these as well. Insert, update, delete. So here's some examples of data definition. Here we're creating a table. The create statement has many forms. All those different things that are in the database have to be brought into existence. So you can create a table. You can create an index. Those are two things we're showing here. Additionally, you can create other things like views, sequences, synonyms. Even users can be defined to the database by creating a user. And there are some other objects that a lot of people don't deal with directly, like you can create a table space. So objects are created with a create statement, and we would say create, and then what kind of thing we're creating, give it a name, and then appropriate syntax to complete the definition. In the case of creating a table, what we're doing is we're defining the logical structure of the table. We have a column, a data type, and a possible integrity constraint. Here we're saying not null, which says you got to give me one of these things. Whatever ID num is, you can't omit it. I have to have one. That's required. In essence, that's what not null means. You can create the table computer, again, similar columns, and a constraint. In addition, we can create something called indexes, and indexes are very much like what you would see if you had an index in the back of, say, a textbook. What you would have there is something that is arranged in order, like all your entries are in, say, alphabetical order, and you have effectively pointers to the page numbers that contain that particular topic, that particular entry in the index. Similar concept applies here with indexes. We can create indexes so that we can find things quickly, or we can create indexes so that we can support integrity. When indexes are created, we make no reference to their use within a query. Remember, SQL is non-procedural. The optimizer decides whether or not to use an index as part of an access path to get to the data. So the table in the database holds the application's data. The index provides a way of associating kind of like a set of pointers or references, just like the index in the back of a book, and it associates that with a table. So an index might be used to improve performance of a query or to enforce database integrity. Again, we don't make the call. The decision to use the index is decided upon by the optimizer. A table could have one index, could have many indexes. It's possible for a table to be defined with no indexes. But whenever an index is present, it gives the optimizer more to think about, an alternative way to get at the data. So if I create a table and there are no indexes, the only way the optimizer can say, this is how I'm going to get to the data, is to say, I'm going to read every single row one by one. That's called a table scan. As an alternative, if I create an index over the employee name column, now the optimizer could do a table scan, or it could use the index of employee names and pick out just those that satisfy whatever condition was specified in the query. So this is an alternative way to get at the data. This is called an access path. So when we make the index, it provides a different option for the optimizer. So we create indexes, and that's how potentially performance can be improved. But it also can be used to enforce integrity, because when you say something must be unique, no two rows can have the same value in a particular column, the database will use an index to enforce the uniqueness. Now, once the index has been created, the RDBMS, in this case Oracle, will automatically maintain the content of the index to ensure that it is synchronized with the content of a table. So if the index is created and I have 9 rows in the staff table, and I create the index over ename, there will be 9 entries. If suddenly I do 2 inserts because I hire 2 new employees, I now have 11 rows in the table. What will happen is the index is going to be updated to reflect and include the names of the 2 new people that were hired. So the index is synchronized or coordinated with the table. And likewise, should I remove a row from a table, what will happen is the index has to be updated in some way to maintain that synchronization. And the same if I update the indexed column. So here are a couple of examples of another piece of data definition. Almost could call this data destruction, because we're not really defining something, but we are altering its content by removing the thing entirely from the database. The drop statement allows us to take an object that already exists and remove it from the database. They still call this data definition, but obviously we're not defining anything, we're removing something. So the drop statement allows us to drop an index, a table. In fact, anything that we can create, there should be a counterpart in the form of a drop to remove the thing from the database should we no longer need it. So we can say drop index. Now if we drop the index, an interesting thing happens. The table still exists. But remember, one of the things that the index did was it provided an alternative way to get at the data, an alternative access path. So if we drop an index, we have then removed one of the access paths to the data. Now, the neat thing is the query optimizer recognizes that and said, okay, now when you run this query, well, I'd like to use an index, but there isn't any available at the moment. So therefore, you go and have a table scan performed for you. So even though you remove the index, you can still get at the data. It might not be the most efficient way because maybe that index was providing very efficient access to the data, but at least you can still get at it. That's pretty neat. And then we have the idea of dropping a table. When you drop a table, obviously if the table has indexes associated with it, the indexes are no longer of any meaning or relevance, so dropping a table has a cascading effect where the indexes on the table will also be dropped. What happens is when you drop a table, all of the data in the table effectively goes away, and the structure and the definition of the table will also go away, and all of the metadata that describes that structure goes away. The system no longer knows about that table. We also can change characteristics of a table. We have a statement called alter. So the alter table statement allows us to add new columns, remove a column from a table, add an integrity constraint, or remove a constraint. There are a few other things you can do, but this gives you the basic idea of what alter can do. Alter table computer, and now we're adding a new column called processor and specifying its data type. Pretty neat that you have the ability to do that kind of stuff. DCL, or Data Control Language Statements. Data control is a way of implementing some kind of security mechanisms or security capabilities within the database. What we're really looking at here is a number of different things. First off, with data control, we can define users who are permitted to access the database. We can also associate with the user or assign to the user privileges or permissions that allow the user to perform various operations. So when we're dealing with creating a user, we are going to be doing something called identification. We're going to assign a name, a login ID or user ID. We're going to deal with authentication. We're going to say how that particular user ID or user account is going to prove who they claim to be. In this case, it would be through a password. And then third, we're going to authorize the user to perform various operations, and this is called authorization. So we have identification, we have authentication, and finally we have authorization. Three aspects of user and security issues within a database. Now, with the create user statement in Oracle, we define a name, and then we can say how the user will authenticate. Very often it's going to be with a password, so we would say identified by, and then put the name of the password. Oracle, like many other commercial relational database systems, supports what's called case-sensitive passwords. So the way we type in the password here on the identified by clause is exactly the way the user, Mo, would have to identify himself and then authenticate using the password exactly that same way. We have a couple of other characteristics here which deal with storage-related management. The table space in which the user's objects would be placed if the user has been given a privilege or permission to create objects that require physical storage, and also a scratch pad area, kind of a sort work area, if the user needs sort work but because they're doing some kind of a sort operation or something, and there's so much data and a little bit of memory to perform it, so it goes out to secondary storage and uses a table space. Now, the privileges or permissions are going to be the next thing that we want to talk about, because this is how we're going to give the user authority to do things. These are data control statements called grant and revoke. Grant, you give permissions to a user or privileges to a user. Revoke, you retract those permissions or privileges from the user. There are two categories of privileges to be aware of in Oracle, what are called system privileges. And here's an example where we're giving the create session privilege to Mo. This gives Mo the authorization to connect to the database, to log in, to create a session. We also have what are called object privileges. The objects could be things like tables. We previously created the pets table, and here what we're doing is giving the ability to select rows from the pets table or insert new rows into the pets table to a user named Mo. Now, Oracle and many other systems use a form of security called discretionary access control. It is the owner of the pets table, or the owner of whatever the object is, that decides which privileges or permissions, if any, are given to a user and to which user or users they've been given. So it's at the discretion of the owner who can do what with that owner's objects. Now, we've given two privileges on pets to Mo. Down here, we revoke the create session. Mo could no longer log on if that was the case. We also revoke insert on the pets table from Mo. So we're showing that you can grant system privileges or object privileges. You can also revoke system privileges, and you can revoke object privileges. The interesting thing about this example is we took away one of the object privileges on pets. Mo had been given two privileges. He retains the select privilege. DML is data manipulation, and I consider four statements to fall into this category. Select, which is data retrieval. Insert, update, and delete, which all affect the content of tables. So we have four operations. Here's how the select works. The select is retrieving data from a table. Select asterisk says, give me all of the columns. You're going to get entire rows. Which rows will you get? Well, after you identify the table from which the rows will be retrieved, you can include a where clause. If you omit a where clause, you get all of the rows from this table. That's the notion of set-level processing that we've described previously. In the next example, we pick a subset of columns and pick exactly those columns that we want to retrieve, and it doesn't matter what order left to right that we display them in and what order left to right they might be physically stored. That's pretty neat that we can do that. We have a comma here between the columns. In addition, we have a where clause that identifies which rows are going to be retrieved. The query processing system will check the name, which is another one of the columns in pets, and if the name is equal to exactly what we put here of Fido, the row will be retrieved. If we have a pet named Spot or a pet named Rover, those rows would not be retrieved. If we have three pets named Fido, all three rows would be retrieved again because of set level processing. Now, we say no references are made to any index in either of these select statements. What characteristic of SQL applies in that case? See, an index could be used, but we're not telling the system how to get the data. We don't say use an index. The query optimizer decides that. So what is the characteristic of SQL that we're talking about here? That characteristic is referred to as non-procedural. We don't specify a procedure or a process by which the data will be retrieved. Now, suppose we had an index and we choose to drop the index. No change is required to the DML statement in the future. So if we run this query now and there's an index, the optimizer may choose to use the index as an access path to retrieve the data. If subsequently the index is dropped and we run this query, the query will still work correctly. It will return the same data, even though there's no longer an index. It will take a different route to get to the data, but the point is it was not affected by the fact that there was a physical change to the underlying data. So what characteristic of a database are we talking about here for this particular situation? Well, this is referred to as data independence. Okay, the other DML statements come up now. Let's take a quick look at these guys. With the other DML statements, what we have is insert to add a row to a table, delete to remove one or more rows from a table, update to change one or more columns in one or more rows. With the delete, we specify in this example a where clause, so that will target perhaps exactly one row or maybe a few rows, but only the rows where this condition is satisfied. Those pets that have a name of Fido, those rows will be removed. Remember, due to set level processing, if we omit the where clause, as we did back here with the select, we got all of the rows in the table. If we omit the where clause with the delete, we will delete all of the rows from the table. The table will continue to exist, but at this point it becomes an empty container. All the data has been removed. So the set level processing is extremely important that you give attention to this point when you're doing data manipulation. Likewise with the update, in this case we're updating a single column, but the where clause is targeting only perhaps one row or some subset of rows in the table. Only those rows would be affected. If we remove the where clause, all the computers now would be selling at the same exact price. Might be a good deal for somebody, but not good for the company, right? Set level processing. Now the next thing we look at is database integrity. With database integrity, we have a concept here of three different things that we want to consider. Entity integrity, referential integrity, and user-defined integrity. These first two of entity integrity and referential integrity are fairly generic. They're common to every relational database. They're actually defined within the theory of relational database called the relational model. The user-defined integrity gives us the ability to kind of customize the content of our tables and how the tables are going to be affected when users work with the data doing DML. And this is something that might be done differently by some companies than others. Like if you work in insurance company ABC, they might have a certain set of behavioral characteristics that they implement. User-defined integrity could be one way to implement that. You go to company XYZ, also an insurance company, they have a different set of rules by which they operate, and there'd be user-defined integrity coming into play there. So it allows each organization to customize the business rules and how they're defined within the database. So that gives us some flexibility. But entity and referential integrity are much more generic in the sense that entity integrity is implemented by a mechanism called a primary key. We'll explain what this is in just a moment. And referential integrity is implemented through a foreign key. Two approaches to implementing integrity within the database. One is called declarative integrity. In this case, business rules are enforced as constraints, defined or declared as part of the definition of the table. Their declaration is part of the syntax of the create table statement. Procedural integrity, on the other hand, this is a set of business rules that are enforced programmatically through typically a database trigger. So a trigger is a special kind of a program object that lives in the database and executes in the database, called a stored procedure. This will reside on the server and it will execute automatically when something called a triggering event occurs. So a trigger executes in response to a SQL data manipulation statement, such as inserting a row, updating a row, deleting a row. So when a trigger is created, you say what kind of event, what's the triggering event, and then you also write the instructions that will be executed automatically by the system when the trigger executes or is said to fire. An alternative to a trigger would be an implementation of procedural integrity within some application program that you or I might write if we were application developers. The problem there, though, is it becomes the responsibility of each application to ensure that the business rules are enforced and enforced correctly. But by creating a database trigger, you are enforcing the business rule in a central location, the database server, right where the data resides. But if you put the application logic to enforce a business rule within one program, and someone else kind of circumvents the process by writing another program but neglects to enforce the business rule, then that business rule is not enforced because this is done outside the database. A trigger, we do it within the database. That's kind of the ideal way to approach it. So let's take a look at the two types of integrity that we were talking about, entity and referential integrity, that are both defined as part of relational database. So when you design a database, you produce what's called a data model or an entity relationship model. It kind of describes characteristics of some application domain or problem domain, and you're identifying the entities. The entities are persons, places, things that exist within that application domain. In the real world, we might have something like employees as entities. We might have departments as entities. So each employee can be distinguished from every other employee. Like you walk down the hall, you can tell the difference between Mo and Larry and Curly, maybe because of their name, but also if you're in human resources or in payroll, the way you might identify them is by some kind of a badge number or ID number. The point is that each entity instance, such as a particular person or a particular place or a particular thing, is distinguishable from other entity instances of the same type. I can tell two employees apart. I can distinguish between two departments. So the real world, these objects have that characteristic or that property. Within a database, they must carry that into the database as well. The mechanism that gives the unique identification to an entity instance is called a primary key. So within each table, we are typically going to define a primary key, which would be a particular column or perhaps combination of columns, the values of which would serve to uniquely identify one row in the table, where each row represents an instance of a real-world entity. That's the concept of entity integrity. Now, a primary key has two very important characteristics. One of them is it must be unique. So the value or values in the column or columns that are designated as the primary key must be unique. They must be guaranteed to identify exactly one row, no more than one row. That's the concept of uniqueness. In addition, the values must be not null. Null is a value that kind of says, I don't know what it is, or the value is missing. So the idea is if you have some column and there's a value in it, that value is going to be used to identify something. If the value is, I don't know, then how can that be used to identify something? So a primary key says that the column or columns that comprise the primary key must contain a value or combination of values that serve to uniquely identify a row, and those columns cannot be null or unknown. That's the concept of entity integrity. Here's how it's implemented within Oracle and within most relational databases. What you would do is say create table, give a name to the table, define each column giving names to the columns, data types, and you can have declarative constraints. Again, this is what we call declarative integrity. We're saying not knowledge required. Additionally, we add a clause that says, hey, this table has a primary key. The primary key is the depth ID or department ID column. And again, we satisfy the other requirement here of it being not null. That's how we would declare it. Most relational databases today, or I should say many of them, implement an index, perhaps automatically, to enforce the uniqueness requirement. Oracle is one of these databases that automatically creates an index to enforce uniqueness on the column or columns designated as the primary key. Okay, now referential integrity. What is referential integrity? Well, when you talk about entities in the real world, such as employees or departments, you'll come to recognize as you understand that application domain that different entity types participate in a relationship or an association. As I look at employee and department, an employee is assigned to a department. That's a relationship that exists in the real world. So many different employees could be assigned to the same department. Here we're talking about something called the cardinality of the relationship. So given one department, there can be many different employees who are assigned to that department. Given a particular employee, that employee is assigned to exactly one department. So we have a one-to-many, or if we view it from the flip side, a many-to-one relationship. Now, when you capture the relationship in the relational database, what happens is you designate a column within the many table. So in our case, it would be in the employee table that will be containing a value of the primary key that exists in some row of the other table. Now, the two tables that we're talking about, one, such as department, has a cardinality of 1 in the relationship, and the other, employee, has a cardinality of many. The 1 table is typically referred to as the parent table, and the many is referred to as the child. So we establish what's called a parent-child relationship between the two tables. So the primary key of the parent gets used as a foreign key within the child. Okay. The primary key, as we said, could consist of more than one column. If that is the case, then when it's used as a foreign key, the foreign key in the child table must consist of the same number of columns. The names of the columns in the foreign key and the names of the columns in the primary key do not have to agree. The names can be completely different, but the data types and sizes must be identical, because a foreign key is going to be prepared to hold any one of the values of the primary key in the parent table. So they have to look structurally the same. So what is the idea here? We say, in general, the values of a foreign key are constrained by the values of the reference primary key. So that's another aspect of integrity. So for example, if we have a department called Department 100, then I could have employees who are assigned to Department 100. But if an employee says, I'm assigned to Department 200, and we look in the department table and we can't find a Department 200, then something's wrong. And what happens is the system will reject the attempt to make the foreign key value for that employee a value of 200. It says you can't do that because the values don't match. You're violating this integrity constraint. So that means people could say that they're assigned to a department only if there really is a department by that particular name or identification. It's also possible that a child table can participate in more than one relationship. And we'll see all of this with several examples when we take a quick look at the academic database that I use in the course a little bit later in our segment here. So here's the principle of how it works put into action. Maybe all of that was absorbed. If not, don't worry about it. Look at the example, and this hopefully will clear things up. I'm creating a table called department. This is going to be my parent. It has a column called Dept ID, which is designated as the primary key. I'm also creating a table called employee. It also has a primary key. Remember, each employee can be distinguished from every other employee. So we have this column called EmpNo, or employee number. That will allow me to distinguish one employee from another. But the real key is that an employee participates in a relationship with a department. An employee is assigned to or works in some department. A given department will have many employees who are assigned to it or many employees who work in it. So the foreign key is inserted within this child table called employee. Not too hard to figure out what the foreign key is. If I already told you EmpNo is the primary key, there's only one other column. Dept ID is the foreign key. We tell the system that. The system doesn't know that. Notice the names are similar, but they're not spelled the same. Remember I said they didn't have to be. In fact, I could even have called this X. Just put the letter X. That would have been okay. Wouldn't have been very descriptive or meaningful, but the database would not have been concerned. The key, though, is that the primary key up here is char length of 4, fixed length character, 4 characters. This is identical in structure, char length of 4. Now, we tell the system that this is the foreign key, not because the name is the same or similar or the data type is the same, but by adding a clause that says, hey, there's a foreign key. This column called Dept ID is playing the role of foreign key. Now, it's a foreign key, which means it's going to match the primary key of some table. What table? I have to tell it which table by saying references department. That's the basic idea of how referential integrity is declared. Now, what are the implications of this? We've suggested some ideas about this already, but the real key comes about when we say, let's suppose I insert a row into this table. You must give it an employee number, and I'll give it a department ID. Notice it doesn't say not null, so that's not required. But I'll give it a department ID. The value that I put in the department ID has to match the value of the Dept ID column up in the department table in some row. I could have a department 100, a department 200, a department 300. Then down here, I would have to use one of those 3 values. If I chose something other than one of those 3, it wouldn't find a match, and the system would say, the deal's off. You cannot create that record. The attempt to insert the employee record would then fail. It would be rejected by the system. That's what referential integrity is about. Here's a little bit different example. We again have department, we have employee, but notice I've extended the syntax here for the foreign key. In the first example, I just said Dept ID references department. I didn't say which column. It will know that it's the primary key. It has to be, okay? Which also tells us something, that department must already have been defined or created in the database before I can create the child table here of employee. Otherwise, it could not validate my declaration or description of the foreign key. Now, in this extended example, what I'm doing is I'm saying foreign key is Dept ID. It references a column in the department table. Specifically, that column is Dept underscore ID. So that's optional. I don't have to say what the column is, but it adds clarity, might add a little bit more documentation to someone reading the create table statement. But by default, it's always going to go to whatever that primary key is anyway. The second part is I'm adding what's called a delete rule. And the delete rule is a very interesting twist on referential integrity. What we had said about referential integrity up to this point is that when you go to insert a row into the child, the value that you put for the foreign key must be found in some row in the primary key of the parent table. Otherwise, the insert is rejected. But there's a flip side to referential integrity that we want to consider. What happens if I've got a row in the department table and I have employees who are assigned to that department? That is, their foreign key value matches the primary key value of that row. Then I attempt to delete a row from the department table. I'm attempting to delete a row from the parent table, and it's the row for which some employees are assigned. Say it's Department 100, and I got 3 employees, Mo, Larry, and Curly, all assigned to Department 100. What happens? Well, if I delete the row from department, what's going to happen to these 3 employees? That depends on something called the delete rule. By extending the syntax here for referential integrity, I can say on delete cascade. What that means is if you delete the parent, take all of the kids with you. The whole family goes. If you delete Department 100, take all of the employees who are in that department and delete those as well. 2 deletes are performed. The delete from the department table for the parent row, and the delete from the child table, the employee rows that match that department. On the other hand, I could say on delete restrict. And if I say restrict, which is the default, which is what applied back here, I said nothing because I was silent. The default of on delete restrict is in play. So if I were to say on delete restrict, what happens is if you attempt to delete a department and there are currently employees who are assigned to that department, the presence of those employees will prevent the delete from the department table. To me, this is just like the behavior of a parent-child relationship in the real world. The child is controlling the behavior of the parent. Now, that's not the deal you probably signed up for. If you have children of your own, you probably didn't sign up for that deal when you had children. The kids aren't going to tell me what to do. I'm going to tell them what to do. But it turns out the child here, the kids, are determining the behavior of the parent according to the delete rule. So on delete restrict says, forget about this guy down here, the employee. When you attempt to do a delete against the department, it's either allowed or disallowed as determined by what the child says, what the delete rule is. Delete cascade says go ahead and delete, but take the kids too. Delete restrict says you cannot delete if there are currently children or employees that reference that. One other option is if the foreign key permits nulls, as it does in this particular situation, you could say on delete set null. Then, in the event that you delete a row from the parent, that will be permitted, but what happens is these guys cannot continue to exist and say, I belong to Department 100 if Department 100 is already gone from the database. But what happens is the foreign key value, the dept ID column here, would be set to null, effectively making these children orphans. They have no parent. They walk around without being assigned to a particular department. So that's the idea of referential integrity from a different perspective. Very interesting concept. The user-defined integrity comes about from the need to be able to kind of do some other things with the data. It doesn't involve uniqueness, it doesn't involve relationship, but it's saying, for example, suppose we had a salary column. We have a salary column for the employee table, and we say, oh, it's going to be an integer. So you say, wow, it's an integer. I'm going to put $500,000, right? That's going to be my salary. That sounds great. Or I'm going to put 10 million. That's going to be my salary. But on the flip side, keep in mind that integers also can be negative. So suppose I said, I got a job for you. You want it? By the way, the salary is minus 50,000. You have to pay me to work for my company. Probably wouldn't be too excited about that. The government wouldn't be too excited about that too either. I don't think you can do that kind of thing. But anyway, the idea is we can add an integrity constraint that says check the salary such that the salary must be greater than 0, or the salary must be between, say, 1 and 100,000, something like that. So the check constraint allows us to specify some kind of a condition that must be satisfied when you insert a row or when you update a row. If the condition fails to be satisfied when you're trying to insert a new row or update an existing row, the insert or the update will be rejected by the system. That operation fails. Unique allows us to add an additional constraint. We say, well, wait a minute, didn't the primary key already address uniqueness? Well, yes, it does, because that's a requirement of a primary key. Well, let's consider another example. Suppose you work in the United States and you work at a company and you're assigned a badge number or an ID number. That might be your unique identifier within the organization. However, another property that you have is you have a social security number. Social security numbers are also unique. Now, both of those are possibilities to be the unique identifier that serves as the primary key. But we tend not to want to splatter social security number all over the place, so we tend to reserve that. And we'll use the badge number as the primary key. Because remember, the primary key is going to appear as a foreign key in other tables, so people will see it. So that's why we don't want to use the social security number. But the social security number also is unique. See, the idea is when the database is designed, the data modeler looks at the application domain and identifies some attribute or column or possibly combination of columns that potentially could serve as the unique identifier. These are referred to as candidate keys. These are candidates for the office of primary key. So maybe in the case of employee, we have two candidates that are running for the office. We have the badge number and we have the social security number. A candidate for a primary key must satisfy all of the requirements of the primary key, which means must be unique and not null. So clearly the badge number satisfies that. Clearly the social security number satisfies that. The election is over, we count the votes, and what happens? The primary key for the table is the employee ID or badge number. So we forget all about social security number. But we don't want to. The point is that the social security number was discovered to be unique. That's another business rule. We want to capture and reflect that business rule within our database. So we can't make it a primary key as well because you can only have one primary key. And a point sometimes of confusion. I just said you can have only one primary key. You can have more than one column in the primary key. That is what is called a composite primary key. But the combination of columns serve as one primary key. So we have badge number as the primary key. Social security number lost the election, but it still has a uniqueness characteristic. We define that to the database as being unique, and that gets enforced within the database. So no two employees could have the same social security number, even though it's not serving the purpose of being the primary key. So another type of user-defined integrity. We also can say that a column value is required. You cannot omit it. And in that case, we're saying not null. So that's the general idea for declarative integrity. For procedural integrity, remember, we can have a complex business rule that is implemented programmatically. And we'll give examples of that later in the course. So that's the basic idea on data integrity. Quite a bit of good stuff there. Hopefully all of that makes sense to you. Well, having seen a number of the concepts that relate to relational database, we're now going to look at some of the tables that we'll be using throughout the remainder of the course. And this is what I'm calling my academic database. There are about 8 or so tables here. When we design a database, that is, when we do what's called data modeling, we capture information about the world we are modeling and then use that information to develop semantically correct data definition statements to implement our design. So the discussion of the examples given here will provide some insight into the type of information that must be gathered and understood during the data modeling process. So we talk about the academic database. As I said, it's simply a handful of tables that I've created. They're not very large, but they're going to serve to allow us to illustrate a number of the important concepts that we've been talking about and some additional concepts later in the course. So these slides are going to show you the structure and the content of a rather small database, but there's some complexity and subtlety within it nonetheless. So the information presented here will explain how the tables are actually defined to the database. This is kind of like the step that follows the data modeling process. We've now decided what the table should be. Let's go ahead and define them to the database. So the statements that we're going to present will illustrate concepts of primary key and foreign key. We've already seen some of that, but we're going to go into more detail with our examples. And additional constraints such as check, unique, and not null. Not null is really just a special form of the check constraint. Now we make the following observations about the sample database that we're going to be presented. The primary keys are unique and not null. That holds for everything that is considered a primary key. Foreign key values must match primary key values. Again, that's the concept of referential integrity that we explained earlier. The check and unique constraints apply business rules from the application domain, the world that we were modeling. So here's some data definition statements for a few of the tables. We start off by looking at a table called the department table. Each row in the department table is going to define one administrative unit at the school. The primary key or the unique identifier is DEPT. That would be the name of the department. We also have information about where that department is located on campus, the building and the room. And there's an additional column here that identifies the faculty number who serves as the chairperson of that particular department. Now, this table, as we see, has a primary key, which is atomic, single column. Likewise, the course table has a primary key, which is atomic, again, a single column. Each row in the course table identifies a single course offered at this particular school. CNO, the course number, is the primary key. We have the name of the course, and we say that's required, not null. The description, every course must have a description, that's not null. These are also characters, but notice the difference here is CNO is fixed length, C name and C description are variable length. We have the credit awarded to a student for completing the course, that's simply an integer. We have the lab fee, how much we charge the student for attending a class on this particular course, and that's a decimal. 5 positions, 2 of which follow the decimal point. We also have the C department column in here, which is required, but the significant point of this is it references the department table, DEPT. So what is C department? It's a foreign key. Every department may be responsible for or sponsor many different courses. A given course is sponsored by exactly one department. This is how we're establishing the relationship between course and department. Additionally, we have another integrity constraint mentioned toward the bottom here that says that the credit must be a value of 1, 3, and 6. We don't have any 2-credit courses, 4-credit courses. We only have 1, 3, and 6 credit courses. The class table. Each row in the class table represents a single scheduled offering of a course. So therefore, there's an association or relationship between course and class. Each course is identified by CNO, as we saw in the course table. Here, CNO is used as part of the primary key. We have a composite primary key. It's the combination of course number and section number that, taken together, will uniquely identify one class or one row in the class table. But course number, when taken by itself, serves as a foreign key to identify the course for which this is a scheduled offering. And notice the delete rule says on delete restrict. If we were to suddenly remove a course from the catalog, hence a course from the course table, a row from the course table, all classes that are scheduled on it would automatically be removed as well because of a cascading delete for our delete rule for referential integrity. We go a little bit further and we have the CIN STR FNO column, which is the class instructor faculty number. This column identifies a row in the faculty table where that faculty member serves as the instructor for the class. so another foreign key. And then we have several other columns here which determine the when and where for the class. When is it going to be presented? What's the schedule? Where will it be delivered? What's the building and room? So you can see nothing in the class table tells you about the number of credits or the lab fee or even the name of the course. That information can be obtained by using this relationship between class and course. This simply has date, time information, location information about where the class will be delivered, but in terms of what the class is going to cover, what department is responsible, that describes the course, and we have to go back to the course table. That's where the foreign key comes into play. So the class table has a composite primary key, not atomic like we saw in the other table. We're using a little bit different syntax here. See, we couldn't really say course number, primary key, class or section number, primary key. That would suggest that we're trying to define two different primary keys. So instead of using that constraint for primary key right here at the column level, we added it at the conclusion of the description of the table. And that's because it's a composite. It consists of multiple columns. Kind of a requirement here to do it that way. The faculty table. Each row in the faculty table represents one faculty member who works at the school. The faculty member is uniquely identified by a faculty number. Each faculty member must have a name. We have an address, the date of hire, the number of dependents, the salary, and then we have a foreign key here that says F department references the primary key of the department table. Remember, the relationship here is each department employs many faculty. A given faculty is employed by one department. So that's why we have the foreign key here to capture that relationship. Additionally, we chose to say that the faculty name must be unique. You cannot have two faculty with the same name. We didn't put the constraint on the column. We added it down here at the end of the declaration of the table. Student. Each row in the student table represents information about one student who's enrolled at the school. Each student is identified by a unique student number. Each student has a name, must have a name, and then also can have an address, phone number, date of birth. We have the IQ of the student, and we have the faculty advisor. This is a foreign key. Each faculty member may advise many different students, but a given student is advised by exactly one faculty member. So this identifies the faculty advisor, a row in the faculty table, for this particular student. Additionally, each student has to declare a major. We say in our database that a major is equivalent to or synonymous with a department. So you major in CIS or you major in philosophy. So the major column is also a foreign key. Notice this one says not null, it's required. Student advisor faculty number did not state not null, so it's possible that a student may not, at some point in time, be assigned a faculty advisor, but they must declare a major. That major is a row in the department table, and we have the foreign key to capture that relationship. Registration. This is an interesting table because what we have is kind of an intersection between student and class. A given student may register for many different classes, and a given class may have many different students who register for it. So to uniquely identify one row in a registration table, we need to take into account three different columns. Tell me the course number, and the section number, and the student number, and that will uniquely identify one row in this table. The remaining data-bearing column in here is the registration date. When did the registration event take place? That's the date data type. Now, we have two foreign keys, because remember the registration event relates to a student and relates to a class. SNO, part of the primary key, but when taken by itself, refers to a row in the student table to identify the student who has participated in this registration event. Additionally, the combination of course number and section number, also part of the primary key, forms a composite foreign key to identify the class for which this particular student or this particular event was associated. So notice we have a 3-column composite primary key, and we have a 2-column composite foreign key. Remember, the number of columns in the class table for its primary key is 2, so therefore we must have 2 corresponding columns for the foreign key to capture the relationship. The staff table. Each row in the staff table represents one employee. This type of employee does not teach classes. Faculty teach classes. This type of employee does not advise students. Faculty advise students. These are administrative folks who work at the school. Each faculty member was identified by a faculty number. Each staff member is identified by their name, the e-name column. Kind of odd we say that's the primary key. What does that mean? Well, it means that no 2 staff can have the same name. Okay, but it also means this is going to be not null. That's implied because it's a primary key. Each staff member has a job title and has a salary and is associated with some department. But notice when we get to department, we don't say anything about a reference. Department is not a foreign key. Say the DEPT column is not a foreign key from staff to the department table. What this means is if you look at the DEPT column, structurally it looks the same as the primary key of the department table, varchar length of 4. That is essentially a coincidence. There's no requirement that it be exactly the same because there's no referential integrity in play here. So this is kind of an odd table, but we did this intentionally so we can illustrate some very important concepts when it comes time to work with SQL and manipulate and access some of the data. We do have one integrity constraint here. The salary of a staff member must fall between $49,000 and $26,000. Probably not a place you really want to get a job at if they can only pay you $49. But anyway, that's a constraint that's applied to this particular table. So we've mentioned these observations already. Here they are once again. Primary keys are unique and not null. Foreign keys have to match primary keys. We also have check and unique constraint, which serve to apply some of the business rules from the application domain. We're using constraints, part of the data definition statements, so this is referred to as declarative integrity. This particular database currently has no database triggers, which means procedural integrity does not apply to this particular database, at least at the moment. So let's look at the content of some of these tables. The department table, here's the primary key. No 2 rows have the same value in the DEPT column. Each department is located in a building and a specific room within that building and is chaired by a particular faculty member. Notice at the moment, management does not have a chair. There's a vacancy there. The rows, again, in any table are returned to us in no particular order if we simply say, show me the rows. For example, select asterisk from department. The left to right order corresponds to the order in which the columns were assigned in the create table statement. So here, to get this data, I did a query such as select asterisk, all of the columns from department, and I had no where clause. Asterisk gave me all of the columns in the same left to right order that was established when the table was created. Here's course. This is our largest table. It has 6 columns and 14 rows. Notice the C department column has values that we saw in the department table. It must, because C department is defined as a foreign key. So we have theology, philosophy, CIS. Those are the only values that we see here. Management is another possibility, but currently management doesn't sponsor any courses. We also have CNO, which is the primary key, and you can scan the data as shown here and verify that there are no duplicates. And then we have a brief description, brief course name, the number of credits in the lab fee, 2 numeric columns. Class. Each class represents a scheduled offering of some course. The course is identified in CNO. The class is uniquely identified by using a combination of the course number and a section number. Notice that the course number by itself does not uniquely identify a row. We have multiple courses for C11, multiple courses for T11. And section number by itself does not uniquely identify a row. Multiple instances of 01, multiple instances of 02. And once again, we've got some information about where and when the class will be delivered. Then we have the faculty table. With the faculty table, we have FNO as a primary key, and again, that's a unique identifier. We have a date for the hire date, an integer for the number of dependents. We have a decimal for the salary, and then F department is a foreign key, and you can validate that here, seeing that we have only values of CIS, theology, philosophy. We have nothing outside of the values shown in the department table. And then we have the student table. SNO is the primary key. And then we have the name, address, phone number, birth date. Notice this is not a date data type. This is simply a character string. This is kind of an older way that people chose to represent date-time data by using character strings. We should really be using date-time data types, but we wanted to show a variety of different techniques here within our database. We also have the IQ, which is an integer, and then we have the student advisor faculty number. Recall, this is a foreign key that identifies a row in the faculty table. Student major identifies a row in the department table. Registration. Remember, this was an intersection between class and student, and we can see class data here, the combination of course number, section number, and we can see student data. What's interesting to note is something like C1101 appears multiple times, but each time it appears with a different student number. Likewise, we might have student number 800 appear multiple times, but each time you see student number 800, you see a different combination of course number, section number associated with that student. And that's a necessity because, again, the 3 columns when taken together must be a unique combination of values. It serves as the primary key. Then the staff table that we mentioned previously has e-name as the primary key, and you can confirm that no 2 employees have the same name. And here, as we examine the department column, notice we have Euclid, who is assigned to math, Archimedes, who is assigned to engineering. Those 2 departments do not exist within the department table, but that's not a problem because we don't have referential integrity enforced here. It's just a coincidence that the values look similar and the column name is the same and the description is the same. Here's a brief description to summarize our tables. We have each table name outside of parentheses, and within parentheses, we give a comma-separated list of the columns. The notation we use is somewhat standardized. We underline the primary key, and if there are multiple columns, all of the columns that constitute or comprise the primary key will be underlined. As a little exercise, consider what the foreign keys are. Kind of review what we went through and take the foreign keys and underline them. And the way we would underline them is kind of a dashed or broken underline, so they don't appear to be part of the primary key. So I'll leave that as an exercise for you. You can pause the video, go back and forth, just to ensure you have an understanding of that. One more interesting thing that occurs here. In our particular table, tables, or database, we walk through it very quickly. But there's another relationship. You may have picked up on it when I described the department table. I said that each row in the department table describes 1 academic unit. DEPT is the primary key. And I also said that DCHFNO, a column in the department table, served to identify the faculty member who serves as the chairperson of the department. If you go back and review the syntax of that create table statement, you'll notice I said nothing about a foreign key. But in reality, DCHFNO should be defined as a foreign key to enforce referential integrity and properly define the relationship where a faculty member serves as the chair. Now, this is not a unique situation that applies to my little database here. It's a very kind of common situation. So, we saw that faculty is a type of employee assigned to department. There's a one-to-many relationship. We captured that by having FDEPT defined as a foreign key in faculty, and it referenced the primary key in department. But faculty plays another role. A given faculty member will serve as the chairperson, that is kind of the manager of a department. This is a one-to-one relationship. A given faculty member may chair or manage one department. A given department is chaired or managed by one faculty member. Given the one-to-one relationship, we have the option of placing the foreign key in either one of the tables. If we give a little bit of thought, what we'll say is, if I were to add the foreign key to the faculty table to say, hey, this faculty member chairs this particular department, what's going to happen for most of the rows in the faculty table? Because most faculty members do not chair a department, for those rows where the faculty member does not chair a department, the foreign key, if we chose to put it in the faculty table, would contain a null value. It would be kind of a waste. On the other hand, every department should have a faculty member. We saw that management at the moment does not. There's a vacancy. That's kind of a unique situation, and it's a short-term situation. That will be remedied, say, very soon in the future. We expect that to be the case. So the point is that it makes much more sense to put the foreign key in the department and identify the faculty member who serves as the chairperson. That's why we chose to put DCHFNO in the faculty, from the faculty table into the department table. But there's only one little problem. We didn't designate it as a foreign key. How do we do that? Well, here's how we do it. It's kind of after the fact. After the fact, we say alter table, another data definition statement. Alter table department, we're going to add an integrity constraint. We'll give a name to it. We'll call it FK DCHFNO. And we'll say there's a foreign key. DCHFNO, a column in department, serves as the foreign key, and it references the primary key, which is FNO, of the faculty table. This will define the second relationship and creates what we call a cycle or cyclic relationship. This is actually sounds pretty simple, but it's very, very complex because we couldn't do this all at once to create the department table and say, here's the primary key and here's the foreign key, and do that all in one shot. The reason is that when you create a table and you specify a foreign key, bear with me for a moment, I'm going to go back and get one of my examples. Here we have the student table. When I create the student table and say student advisor faculty number is a foreign key, remember the data type of the foreign key has to match exactly the data type and the size of the referenced primary key. So here I'm saying it's char length of 2, and it references the faculty table's FNO column. Well, how does the system know if this is valid? Is the primary key of FNO, or the primary key of the table of faculty, which is FNO, is that a char length of 2? The way the system is going to find out is it's going to go query some of the metadata about the faculty table. Therefore, the faculty table must already exist before I can create the student table and make this relationship. Similarly, the department table must already exist. It must already have been defined before I can put the foreign key in here for student major. Otherwise, the system can't do the validation. This is why, if we go back a little bit further, when I created department, I said, here's the primary key, but I could not say DCHFNO references faculty because I have not yet declared faculty. creating the department table would fail if I tried to do that all in one shot because faculty doesn't exist. And I can't very well go ahead and say, let's create faculty, here's the primary key, and here's the foreign key that references department. I can't do that if I've not yet created department. So how could I ever get these two tables created? The way we do it is we withhold a little bit of information here and say, I didn't tell you this. I'm kind of keeping a secret from you that DCHFNO is a foreign key. No problem. System allows me to create this table. Then when it comes to faculty, I can define faculty completely because it can validate my definition of the foreign key against the primary key of department. And then when we get up here, after the fact, after I got my tables created, I go ahead and say, oh, by the way, I forgot to tell you, department has a foreign key, and I add it as a third step. Now it can validate this reference. So the alter table is very handy, but the cyclic relationship can be a bit tricky to deal with in creating the table. It can also be a bit tricky to deal with when you go and populate the data. Because remember, when you're dealing with referential integrity, if you go and insert an entire row in the department table and faculty has not yet been populated, then when you assign a faculty number, it's going to be rejected because it can't validate it. So if you try to insert an entire row into the faculty table, you'll have to give me an F department to identify the department the faculty member is assigned to, but you can't do that if you haven't created that row either. So it's kind of a catch-22. In creating the tables, it's a catch-22 in populating them. And I'm not going to tell you the solution to that just yet, because I want you to stay tuned in, kind of sit on the edge of your seat. We'll talk about that in a later video. Okay, one more very important concept about relational database systems is what we call the system catalog. Oracle refers to it with a slightly different name. They call it the data dictionary. Regardless of what name you choose to use, it stores metadata. Metadata is data that describes other data. For example, when I go and look at the department table for an application, I'm going to be saying, well, what's the name of a department? What building is it located in? What room? Things of that sort. I'm looking at the content of the table. But I have to also define to the database what are the names of the columns? What are the data types of the columns? What are the sizes of the columns? Which column or columns make up the primary key? Which column or columns make up foreign keys, and so forth? That's data that describes the table. It's not describing the content of the table, it's defining the structure of the table. So we call that metadata. There are other forms of metadata, but that kind of gives you a taste or a feel for it. So that is some of the information that's stored in the system catalog or data dictionary. So later on, when we run a query against the department table and say, hey, give me the value in the DEPT column and give me the value in the DBLD column, the system can say, oh, those are both valid columns in this table and they're both character strings. So it can do that kind of validation and then go ahead and run the query. So the data dictionary stores all kinds of metadata. And in Oracle's case, we've given you a little bit of an example with some detail as to what it stores. It stores information about the database users, the user ID. Remember we talked about identification, authentication, and authorization? So it has the identification here. It also has information about authorization. It also has somewhere within it the authentication. Is the user validated or authenticated by a password? If so, what's the password? Oracle has that stored internally somewhere within the data dictionary or catalog. Structure of schema objects, names of tables, views, indexes, names of the columns, data types, integrity constraints, and so forth. All of that is part of the metadata stored in a data dictionary. Integrity constraints, primary key, foreign key, other types of declarative constraints. Also, PL/SQL objects. PL/SQL is a programming language used in Oracle, and you can use that to define stored procedures, packages, database triggers. So database triggers, remember, are a way of implementing procedural integrity. But information about all of these program units or program objects would be stored in the data dictionary. Storage allocation. The system can track how much disk space is being used for this table, for this index, and so forth. And it can do all kinds of administrative stuff using that data. And there's a lot more, but it gives you the idea that there's a wealth of information available in the form of metadata within the system. The data dictionary is created when the database is created, and it's used immediately thereafter. If the data dictionary somehow became corrupted, or the disk that it was on was inaccessible, your database couldn't operate, because the data dictionary is consulted every time someone runs a query or performs an operation against the database. So it's a very important collection of metadata. How is it used? Well, we've given some suggestions to this already. Primarily, it's used by the database management itself. Every time you perform a data definition statement, create, alter, or drop, the metadata is updated. Each time you do a DML operation, select, insert, update, or delete, the metadata is consulted to examine the table and the columns, make sure that you're referring to these proper names, using correct data types, and also it goes and looks at authorization, making sure that you're able, that you have the authority to do a delete or an update or insert or even a select. And, of course, validates the data types. We're not going to take a name and do arithmetic with it. The system can say, hey, that doesn't make any sense when it sees that the definition of the column is character, and you're trying to do an arithmetic operation. So that gives you a pretty good feel, I think, for how the data dictionary would be used. A real neat thing is, because the data dictionary is stored as tables, we can actually query the data dictionary if we're curious about things or want to inquire about some particular aspect of how the database is operating. Now, the way the data dictionary is organized is there are three different levels for the most part. There are user views, views prefixed with USER, views that are prefixed with ALL, and views that are prefixed with DBA. So the names actually begin with these little phrases. User tables, all tables, DBA tables are examples of different levels of information. The user views contain information that relate to the current user. So if you were to query user tables, you would be seeing the tables in your schema, the tables that you own. Even though there could be hundreds, thousands of other tables out there, you don't see those because you don't own them. The all shows you all of the objects that pertain to the current user. So if you were to say all tables, you'll see the tables that you own, the same thing that you would see in user tables, plus you'll see additional tables to which you've been granted access by other users. You still, again, may not see everything in the database. The DBA level is accessible only by a privileged user who has DBA authority, or some subset of that. The DBA level views effectively show the entire database. So there are three different levels here. The data dictionary is self-describing. There's a data dictionary view called dictionary. And if you say select from dictionary, you'll see in each row the name of a data dictionary table and some kind of description, some comments to give you some heads up as to what that table is used for. Additionally, each one of the columns of each table can be documented and is documented to some extent within the database. So in DICT columns, each row contains the name of the table and the name of a column within the table and some comment to describe what that column is used for or what it means. Here is a quick little example. I'm selecting the comments column from DICT. What is DICT? DICT is actually an abbreviation for dictionary. You can, if you've watched me type, and you probably haven't yet unless you've watched some of my other videos, I'm not very good. I tend to make a lot of mistakes. And if I've got to type the word dictionary, good chance I'm going to get it wrong. But if I type a simple four-letter DICT, chances are pretty good I'm going to get it right. So fortunately, DICT is an abbreviation that has been made available to us. Technically, this is what is called a synonym, and I'll explain synonyms in just a few minutes. So here I'm selecting the comments column from DICT, or alternatively, I could have said dictionary, spell it out, where the table name is dictionary. And this gives me a description of data dictionary tables and views. Unfortunately, even though Oracle has a lot of space in the comments column, they are very curt, very brief with their descriptions, and some of them, it's like, well, why did you even bother putting a description? I could have figured that out from the name. It would have been nice if they had been a little bit more thorough, a little bit more comprehensive in providing meaningful descriptions. Then we have a simple query against dictionary columns, getting the name of a column and the name of the comments for a particular table, and here we see the descriptions. So it's actually a nice little feature, and I just kind of wish that Oracle had done a little bit more thorough or comprehensive job in utilizing it. Here are a couple of examples of queries we might run against the database to use the data dictionary. Here we're selecting the name of a view and the text. The text is the stored query. We've not yet really talked about views. We'll talk about that later. But the idea is if I want to see what the definition of a view is, and it's a view that I own because it's in user views, I can run this query and I can get definitions of the views that exist within my schema or the views that I own. I can get a list of all the tables that I own. Again, user table. I can determine the schema name or the user name that owns the table and the names of those tables to which I have access. Notice I'm querying all tables. So this would show me all of the tables in my schema, if there are any, plus all of the tables in schemas of other users for those users who have granted me the authority to access their table in any way. Could be select, insert, update, delete, but that doesn't say in this table, but it will at least tell me that it's a table to which I have some access. So a summary of the data dictionary. We say that the data dictionary contains information about the logical structure of application tables, including its own structure. It's self-describing. The data dictionary contains information about the physical structure of the database. And every time a user performs an operation in the database by executing a SQL statement, the data dictionary has to be consulted. It determines if the table is a valid table, if the referenced object is either a table or a view, if the valid column names were specified, or if you gave me a bogus column, if the user is authorized to access the object, if an index exists on the table. So this is where query optimization starts as well, with the data dictionary being accessed. Remember, it's the query optimizer that figures out how to access the data, because SQL is non-procedural. So when you run a query, it's not only doing validation in order to be able to run the query in terms of, okay, the syntax is correct, it's a well-formed expression in SQL, and authorization, you are permitted to perform the operation you're trying to do, but it also looks at some additional metadata to construct an execution plan, determining what alternative access paths might be available in terms of the presence of indexes, and also evaluating those to see which approach might be more effective, more efficient, less resource consuming. And as promised, here we are with synonyms. A synonym is a type of an alias. It's a database object that gets created, and it's an alias, or as the name itself says, a synonym for something else. It could be an alias or a synonym for a table, a view, a snapshot. A snapshot is an alternative name for something called a materialized view. We'll talk about that down the road at some point. Or a sequence, or a procedure, or a function or package, various program objects. So a synonym itself doesn't require any physical storage in the database, as does a table or an index. The association of the synonym with a table, a view, or whatever the database object is simply recorded in the data dictionary. So you don't need any kind of disk space or quota in order to be able to create a synonym, but you do need the create synonym system privilege. So what's the purpose of synonyms? Well, they could be used to mask the name and owner of an object. They could provide what's called location transparency if we have a distributed database. They could simplify SQL statements because it allows us to come up with aliases that might be a little bit shorter than table names, and we don't have to qualify the table name with the schema name, for example. Okay, a synonym can be public or private. Public synonyms can only be created by a database administrator, and then they can be available for use by everyone within the database. This requires a special privilege called Create Public Synonym. Private synonyms would be a synonym that perhaps you or I might be able to create, provided we had the Create Synonym privilege. We don't need Create Public Synonym, but we do need Create Synonym. And these would be owned by whoever creates them, and they present aliases or synonyms for other database objects. The syntax for creating a synonym: simply create synonym, give it a name. That name must be unique within the context of where it's going to fit. So if it's a private synonym, you cannot have two synonyms with the same name in your schema. If it's a public synonym, then we cannot have two public synonyms with the same name, because those are kind of global in a sense. And then we create the synonym by associating it with some database object. If we no longer need synonyms, we can remove the definition or the association of the synonym and the object from the database. The object itself will remain there, but the synonym goes away. Hence, the association goes away. So when a synonym is no longer needed, we can use the drop synonym statement. If it's a public synonym, you must say drop public synonym. And again, you have to have DBA authority, or you must have the drop any public synonym privilege. Here are some examples. We're going to create a public synonym called department for the department table that resides in Mo's schema. Users would then be able to say select from department without having to say select from mo.department. That's where it might simplify the SQL queries a bit. We can give users authority to use the public synonym by granting select on, say, department, the name of the synonym, to public. Notice that what's happening is that indirectly, even though we're saying grant on the synonym, we are granting select on mo.department. If a user knew that department was actually an alias or synonym for mo.department, and the user had the authority to select from the department synonym, they could then go ahead and actually say select from mo.department if they so desired. But that kind of defeats the purpose of the convenience that synonyms provide. Here's an example of getting rid of that synonym later on. Because it was public, we have to say drop public synonym department. Here's a private synonym. We're creating a synonym called C, very short name, which is an alias for mo.course. Let's summarize what we've talked about. Talked about quite a bit in this lecture. We showed how some database concepts, kind of the theory, actually work within a commercial product, kind of putting these into practice. We provided working examples and descriptions of SQL statements that are used in preparing a database for a user or application activity. We talked about data definition statements, data control, and data manipulation. We examined how the DBMS addresses data integrity through two mechanisms: declarative constraints, which is called declarative integrity, and we also mentioned there's an alternative called procedural integrity, kind of a programmatic enforcement of integrity constraints or business rules. We introduced some very basic syntax of the SQL select statement, kind of give you a taste of that. We have lectures where we're going to go into that in great detail, but here you get a little taste of it. We also explained the role and basic structure of Oracle's data dictionary, which again, most other systems would refer to as the system catalog. And we explained how metadata is stored there. We explained the role of the metadata and the nature of much of that metadata. So hopefully that gives you a pretty good feel for how this commercial relational database product works. I chose Oracle but I could just as well have chosen SQL Server or DB2 or MySQL, and this lecture would have been very, very similar, just minor tweaks. So the concepts I presented here are not entirely unique to Oracle. So hopefully that gives you some comfort if you say, well, I really want to work with SQL Server. Now, next up on the agenda is we're going to talk about Introduction to SQL. Okay, that's going to be where we're going to look at SQL statements in some detail. We're going to be doing query writing. We're going to be looking at the select statement. So I hope you enjoyed the video, found it useful. If you want to offer any comments, please do so in the comments section. And if you've not yet subscribed to the channel, this might be a great opportunity to do that. Remember again, there's no cost for subscribing. It's just a way of you showing kind of approval of what we're doing and that you want to see more of this stuff. Okay, and it'll also keep you apprised of when new videos have been posted. So once again, thanks for watching.